house, Professor Albin Gasiewski, in the ECE department here at CU Boulder. Professor Gasiewski received his master and bachelor degree from Case Western Reserve University, also his, in engineering and mathematics. He received his PhD degree from MIT. He then went to work as a faculty member at the Electrical and Computer Engineering Department in Georgia Institute of Technology. He then changed from academia to national lab and worked at NOAA until 2005 when he joined the faculty here at Boulder. He's the director of the Center for Environmental Technology, and here today to tell us about the passive microwave imaging of the environment, past development, and future systems. So, welcome.
Thank you. Well, thank you again for the invitation. The prospect of talking about imaging really gave me an opportunity to think about environmental observation and how imaging plays a role in it. And I'm going to try to describe a lot of different ways that imaging plays a role, not just two-dimensional imaging, but three-dimensional imaging, and even four-dimensional imaging. And I'm going to be focusing on a long-running set of research activities, really activities that have been going on for probably about, depending upon whose calendar you're looking at, 30 years or so, give or take, on the topic of passive microwave imaging of the environment and how what we're doing in the laboratory and in the field is leading to new capabilities that we're going to be putting in space in future years. So this will be a discussion of past developments and future systems with regard to passive microwave imaging of the environment. And I'm going to try to cover four primary topics. I'm going to talk a little bit about microwave emission and surface emission, microwave atmospheric and surface emission, which underlies everything I'm going to talk about. So some of the basic physics really need to be at least partially touched in order to appreciate some of the imaging that we do later. Then I'm going to talk about airborne imaging radiometry, how we take these principles and we translate it into systems that provide us insight into what we could learn from space. I'm going to talk about calibration, and calibration is central to what I'm doing over here, and it provides requirements, it levies requirements on our imaging that really far exceed most kinds of imaging. Looking at the environment, whether it's through a passive microwave system or even many other types of systems, radars, lidars, etc., it demands a precision, because these environmental signals are oftentimes rather weak. It demands a precision that, again, typically is far more significant than what's usually used in the laboratory. And then I'm going to talk about where we want to go with this work, which is microwave imaging and sounding from geostationary orbit, and why that's important. Let's first talk a little bit about the physics of microwave atmospheric and surface emission. And the physics are embodied to a great extent in this set of curves that describe what we call the opacity of the atmosphere. This is how well you can see through the atmosphere at radio wavelengths. And this set of curves runs from about 2 gigahertz, where the atmosphere is very transparent. It's even more so down at radio waves, and at least until you get to HF and low HF ranges where the ionospheric effects become significant, all the way up to a terahertz. And this is a rather interesting region because it goes from virtually completely transparent. This is an opacity of basically less than 1/10 of a dB. That's pretty transparent. All the way up to places where the atmosphere is very opaque, 10 to the 5th decibels. 10 to the 5th decibels, mind you. We know what a decibel is. Of course, 10 decibels means a factor of 10 loss in power. So you can imagine what 10 to the 5th decibels is. You basically can propagate a wave on the order of a millimeter or so before you start losing its energy. So there's a very nice range, and depending upon where we go in this spectrum, we can again get very transparent results, very opaque results. We can also look for the behavior of certain species that are important in the atmosphere. And from the standpoint of weather forecasting, the most important species in the atmosphere is water vapor. Water vapor carries a lot of energy with it. It literally dictates what's going to be happening from the standpoint of transport of energy, phase transitions from the vapor phase into liquid, into solid as well. And so it's a very important variable. Well, it just so turns out that happily we can observe water vapor with reasonable amounts of opacity at a lot of different places in this spectrum. We can also observe, for example, oxygen. Of course, oxygen isn't all that interesting in the sense that it's pretty well mixed and we know pretty much how much oxygen is around us all the time. But on the other hand, when you measure the emission from oxygen, you're also able to measure its temperature. And so it gives you the opportunity to profile the temperature in the atmosphere the same way you would profile it if you, for example, launched a weather balloon. So just by looking at key frequencies, for example, on the side of this absorption line or that absorption line of oxygen, or up here there's another one at 424 gigahertz, etc., you can then profile the temperature in the atmosphere. Now, there are a lot of things you can do with this spectrum. If you look at low frequencies, you can observe down into the surface, little opacity. You can observe down into the surface of the Earth, and you can actually measure the amount of liquid water in the Earth. The way this works is that the more water you have inside soil, the more reflective that soil becomes to frequencies down in this range. And therefore, the more you will see in looking down at the soil, cold space. If you look directly up at cold space, what you'll see is a temperature of around 2.7 Kelvin. So if you look down on the Earth, what you're seeing is that 2.7 Kelvin cold temperature reflected, and the variation in the amount of moisture in the soil will change that signature you see quite significantly. And I'll show you some examples of how we use that. You can also measure sea surface temperature by similar means. The warmer the ocean, the more emission you see from it. This little looks like a backwards check mark here in the Gulf of Mexico is actually the cold wake of Hurricane Katrina. This was the result of the hurricane passing over the Gulf and literally drawing up cold water from deeper portions of the Gulf and taking away heat from the surface and leaving a wake behind it that was up to 4 degrees Celsius colder than in front of it. So it's proof positive that the energy of a hurricane comes from the ocean, from water essentially. We can also measure ocean winds. The stronger the wind is on the ocean surface, the more rough the ocean surface is. And the rougher the ocean surface is, the less reflective it is, and therefore the warmer the temperature you see. You can also measure the direction of winds on the ocean surface. You might ask, well, how do we do that? Well, just so it turns out that the waves themselves are preferentially aligned with the direction of the wind. In other words, the waves are orthogonal, I should say, to the direction of the wind. And if you're looking at wave structure, you'll get a different temperature depending upon what azimuth you see that structure with. This was one of those techniques where nobody really appreciated it or tried to capitalize on it until about, the late 1980s, where this subtle signature of wind direction was found in satellite data. And rather quickly then, we developed systems using polarimetric techniques that are much, much more able to measure that wind direction with high sensitivity. And in fact, that's now part of our the suite of instruments that's going to become part of our national forecasting satellite system in this decade. Other things we can measure, water vapor. I talked about that earlier. The more water vapor, the more emission you'll get, essentially. We can also measure things like snow cover at high frequencies where snow scatters a great deal. We can determine the amount of snow on the ground and to some extent its depth just by measuring that reflected background signature, that reflected cold background. I mentioned earlier that if we look at various oxygen lines, we can measure the temperature of the atmosphere. We can also distinguish between sea ice and open water very easily. This is actually fairly valuable to do. You think this is maybe not so important because why don't you just take a picture of the ice? Well, it turns out that much of the Earth whereby we want to see that ice is shrouded by clouds. You can't see through clouds. You can't see through them with the visible, and you can't see through them very well with the infrared. When you go down to microwave frequencies, a factor of 30 or so lower in frequency, in other words, a wavelength 30 or so larger than infrared and visible, you can see through those clouds quite well. So it allows you to map sea ice that you otherwise couldn't see very well, and in fact that's one of the ways we get our estimates of the overall coverage of sea ice in the Arctic through passive microwave mapping. We can also observe rain quite well because, as the next slide shows, the Rain itself, whether it's in liquid form or whether it's frozen into ice, causes, again, a rather interesting and very useful degree of absorption or scattering, depending upon the frequency. At a low enough frequency, we can see through almost any rain event that's going to occur. Generally speaking, these numbers, when you multiply them by a distance, are going to be so small they don't matter. But as you go up higher in frequency, you can even pick frequencies where you're more and more sensitive to rain, to an appropriate degree, that is, and therefore you can use passive microwave observations to actually measure the amount of rain occurring, or cloud cover for that matter. So there's a rather useful range of frequencies, again, around a gigahertz to around a terahertz, where we can do a lot of environmental imaging. Now, we can do this imaging either from satellites or from aircraft. And the difference is a matter of resolution and a matter of cost. Of course, anytime you put something on a satellite, there's a rather steep cost associated with that, with the launch. When you put something on an aircraft, typically that cost is lower by about a factor of 1,000 or so, give or take. So there's a lot of incentive to be able to put these systems, as you're developing them, on aircraft first. So I'm going to talk about that today. The resolution you get is also much better. Up on a satellite, you're fairly far away, typically several hundred kilometers in altitude. On an aircraft, you're typically 10, 20 kilometers at most, or even down to perhaps 100 meters. And so the spatial resolution with which you can see this set of environmental events is a lot different from the two. So I'm going to talk about how we've gone from aircraft to satellites in various different environmental observation modes. So, airborne imaging radiometry, well, this came about basically in the mid-1970s. As soon as people recognized that they could do interesting things with radiometers, they started building these and putting them on aircraft. And this is kind of a rough history of the various different instruments that were built up to around 1995. The first one, in the US at least, was built and flown in 1978. Then several others followed that. They all had different frequencies. They all started pushing higher and higher in frequency and developing more and more sensitive calibration. Here's one in 1992 where we first developed a channel with a wavelength smaller than a millimeter. And there were a lot of accomplishments that came out of these. I'm just going to point out some of these accomplishments. This is a picture of one of those instruments. This is an early instrument, and in fact one that I built for my thesis way back in the early 1980s. And it shows a scanning mirror which allows a microwave radiometer to be scanned across track of the aircraft. So as the aircraft flies forward, this is scanning across the track of the aircraft, essentially forming a raster, essentially providing an image. This actually was the first airborne radiometer to have any publications coming out of it, so I'm rather proud of that. And here's one of the pieces of data that came out of this. This is a set of what we call strip map images, and this is the flight direction up and down the page. Across is, of course, across the track of the aircraft. And what we see here are images at various different frequencies. Each of these channels is a slightly different frequency around this 118 gigahertz oxygen resonance. And in fact, this channel 7 is actually kind of far from that resonance, about a gigahertz away. And this channel 2 is actually close to that resonance. And what we see from aircraft looking down is channel 2 shows a nominal brightness temperature. And then when we fly over rain cells, what we see is reflection of cold space in the top of that rain cell. The top of that rain cell basically contains ice. That's what happens when water is convected high enough into the atmosphere, it turns into ice. That ice reflects the cold background very well. We get a nice cold signature. And the further we get away from that line center, out here to channel 7, the more deeply we can see into that atmosphere, and therefore the stronger is the signature of that rain cell. And there are a lot of useful things you can do with this. We demonstrated for the first time that you could profile the temperature of the atmosphere, and you could actually improve your estimate of the temperature of the atmosphere, relative to a priori, that is, by around 50%, in other words, reduce it. And you can also measure things associated, parameters that is associated with the convection. in particular the top of the cell. The top, the higher it is, the colder it is, the more liquid turns into ice, and therefore the more reflectivity. By the way, this little image here was hammered out on a line printer. So those of you who are complaining about not having the right equipment, recognize that you can do a lot with just simple equipment as well. In the early 1990s, we built another instrument. This was in conjunction with NASA. And this allowed us to explore higher frequencies. For the first time, we had a radiometer that operated at sub-millimeter wavelengths. We're pushing our way up that spectrum and observing clouds with greater sensitivity and observing water vapor also with greater sensitivity. And one of the questions was, well, what can you observe as you go higher and higher in frequency? Here, for example, are three frequencies, 150, 220, and right around 325 gigahertz. And it looks like you pretty much see the same thing. Well, do you really? Well, you can find out whether you see the same thing by essentially looking at every pixel in this image, which is now a 3-vector, in other words, 3 components to it. And you can do a principal components analysis, or also known as Carhoonen-Loewe decomposition. And that gives you an estimate of the number of degrees of freedom. Now, it turns out that that's even not a conservative way to do this. It's better to do what we call a nonlinear Carhoonen-Loewe decomposition. And that actually shows you now, when you look at the coefficients of the KL decomposition, K1, K2, K3, that you actually get more than one piece of information from this set of maps. K1 is often very different in morphology than K2, these two images, which is often very different, which are, I should say, often very different in morphology than K3. So there actually is information in the spectrum, not just in the gross perturbation of the spectrum, but also in the tilt of the spectrum, and even in the curvature of the spectrum. So there's information to be gained, more than what meets the eye, at least in the simple brightness image. So we kept on working on cross-track imaging, and we finally found out that we really can't take advantage of polarization when we study images in the cross-track mode. Why is that? Well, all of these images so far had a 45-degree mirror that was spun around an axis with a motor, and that mirror reflected the beam down to the Earth and allowed you to do your cross-track scan. Unfortunately, the other thing it did was it allowed the polarization of the beam to rotate during the scan. So for part of the scan, you were looking at vertical, then you were looking at mixed vertical and then horizontal, etc. And that made image interpretation very difficult. So what we realized in the early 1990s is that we had to have a system that would allow us to image with distinct vertical and horizontal polarizations. And that's what led us to what we call a conical scanner. Now, a conical scanner is a lot more difficult to build than a cross-track scanner. A cross-track scanner, you can set this little mirror up inside a nice, comfortable little compartment inside an aircraft, and you can scan your beam outside a slot. That works pretty easily. With a conical scanner, you've got to have your antenna at times during its scan facing the slipstream. And so all of a sudden we went from dealing with putting a sensitive radiometer inside a nice cozy compartment in an aircraft to one where the radiometer had to be out in the slipstream of the aircraft. And if any of you have put your hand out the window of a car going about 60 miles an hour, you know how much force there is. Well, that force goes as the velocity squared, and you can now imagine going from 60 miles an hour to, say, about 400 miles an hour. And you'd recognize just what we had to do. We had to take literally the most sensitive radio receivers you can build. These radio receivers are meant to observe the thermal noise in the environment, the naturally emitted thermal noise. They are, as I'll talk about in a little bit later, they have precisions, gain precisions on the, not decibel, but milliBel level. And we had to have them sitting there scanning around once every several seconds in a slipstream going by at 400 miles per hour. So that was quite a challenge. It turns out we did it though, and how we did it was rather simple. We built this thing like a brick house. That's a quote from one of our NASA colleagues. Now, this conical imaging radiometer, as we call it, allowed us to put a lot of different frequencies into here. In other words, radiometers operating at different frequencies. And we built various versions of this that had different sets of bands, but we always tried to hit a broad range of the spectrum and observe at fairly important frequencies, in between the lines and at the lines, if at all possible. Because what happens when you just move from, let's say, 89 gigahertz to 90 gigahertz? It's not that much. But when you move from, say, 89 to 37, there's almost a factor of 2 change in wavelength, actually more than a factor of 2 change. And that factor of 2 change gives you very different effects from the standpoint of both the atmospheric contributions as well as the surface contributions. So we built these at a variety of different frequencies, some of them up even at a very, very high frequencies, sub-millimeter wave range. And we also built them to allow not only imaging in vertical and in horizontal. We could do that now because the antennas were always fixed in their polarization basis angle. But we also measured the third and the fourth Stokes parameters. I'm not going to talk about those today other than to say that this instrument that allowed us to measure the third and the fourth Stokes parameters led to the development of the Naval Research Laboratory's WindSat satellite. And that WindSat satellite is the instrument that is now measuring ocean wind direction and is a pathfinder to what we'll be using in current satellites launched in several years for exactly that operational variable. So, what does this instrument look like? Well, these are pictures of it. Basically, these are the radiometers inside their scan heads. These drums are able to be rotated both in azimuth and in elevation. So you think of it like a telescope mount, but upside down. And we have the ability to fully rotate these, even to rotate them to look up into the aircraft where we place calibration targets. And I'll talk about those for a moment because the calibration targets are particularly important. Again, we're operating receivers that are sensitive at the milliBel level, and so calibration is almost everything in this business. This is those units sitting on an aircraft. This is a typical aircraft that we fly these on. This happens to be the NASA P3. These instruments fit on, I think last count was 7 different aircraft, depending upon what kind of configuration you want to run. We've operated on P3 aircraft, DC-8 aircraft, high-altitude aircraft, even UAVs. What do we get out of them? Well, here's some imagery of soil moisture. Now, let me spend about 1 minute talking about how we got this imagery. We took our aircraft and we flew back and forth, and you can see the sort of edges of these scans here. We flew back and forth, and as we flew along, we operated in conical imaging mode. So the beams of the radiometer were moving across the ground in sort of a stretched corkscrew fashion. And we were sampling fast enough and scanning fast enough, so we essentially had those beams overlapping by, around their 3 dB width or so, give or take. It was almost Nyquist sampling, not quite. Strictly speaking, to be Nyquist sampling, you need to be operating a little bit closer. The angular spacing is lambda over 2d, where d is the antenna diameter. We're operating pretty close to that. And what we did is we observed, in particular for this set of maps, at 6 gigahertz. Now 6 gigahertz is, if you think back to that first slide, a fairly low frequency, and the atmosphere is almost perfectly transparent, but the soil itself is reflective, and its reflectivity depends upon how much moisture is in it. So if you have, for example, a lot of rain that has occurred, that soil builds up moisture rather quickly. It's like a sponge, and that moisture reflects the cold background of space. On the other hand, if you have a period where there's several dry days, that moisture dries out, and what you see is a higher brightness temperature. You see a brightness temperature that's more close to the terrestrial temperature. So what we developed is a set of maps of volumetric soil moisture. And volumetric soil moisture typically ranges between around 5% for very dry conditions, up to around 50% where the soil begins to liquefy. And this happened to be over central Iowa. And this is a range of about 100 kilometers by about 50 kilometers. And we were able to obtain maps of soil moisture with a spatial resolution of about a half a kilometer, 1 kilometer actually, a little more closely. And 1 kilometer turns out to be about the resolution associated with a single section of farmland. If you go and drive around in the Midwest, you'll find out that land is sectioned up in pretty much square mile units. And so this is roughly the resolution by which people perform agriculture. Now you can see in this imagery, this was obtained on June 25th, a couple days later, 27th, a couple days later, etc. The things do vary. Not too much in these first few frames. But what happens over here is actually the previous day there was a thunderstorm that deposited about 1/2 inch of rain, typical for the Midwest, and it left its signature in the soil. And we can see it very clearly there as soil that got up to around 40–45%. Then we had a period where things dried off. There was some scattered rain, and also then a little bit later some more intense rain and widespread rain. Now rain is very important for agriculture, so if this kind of information was available daily to people who had to otherwise expend resources pumping water out of the ground or otherwise using other sources of water, you can imagine how valuable this kind of information would be. Now mind you, this is also observed from aircraft, so it's not anything of the type that we can get from satellite today. Here's another observable. This is snow water equivalent. In other words, it's the amount of water in millimeters that you'd get if you took a vertical column of snow and then melted it. Typically, snow occupies a density of around, give or take, 10 to 20% of that of liquid water. So a column of snow a meter deep typically turns out to be around 10 or 20 centimeters of liquid water. Well, this is a liquid water, snow equivalent liquid water map, that is, of an area in Colorado, the North Park area. And what we did is we flew the aircraft again back and forth, and we took the observations, which in this case were at 18 and 37 gigahertz, different frequency for a different environmental variable. And we developed an algorithm based upon NASA's use of satellite data that gives us the snow water equivalent. And then we georegistered it. And you can see very clearly that in the valley over here, where it's typically a little bit warmer, you don't have as much snow. On the other hand, over the mountain peaks, you have a lot. This was able to be done with a spatial resolution of about 100 meters. We don't have this today regularly. It was done because we were able to go out there with an aircraft and expend a little bit of money and time flying around. But you imagine how useful this would be from the standpoint of water management, to know how much snow you have to this kind of spatial resolution in all these various watersheds. Here is that same data that we have obtained over 3 areas from our aircraft, compared with the satellite data that NASA provides using precisely the same principle. They take the difference between 18 gigahertz and 37 gigahertz, and they scale it, and they get a snow water equivalent. Now, why are 18 and 37 so important? Turns out it has to do with the size of snow crystals themselves, the size of snow grains. This wavelength at 37 is about a centimeter. 30 gigahertz is 1 centimeter. 37 gigahertz is just a little shorter than a centimeter. And it turns out that that wavelength is pretty close to the scale of the grains inside the snow. And so when you have snow build up, those grains scatter quite significantly. They reflect the cold background of space, and you get a good signature. If you then compare it with what you'd get at a lower frequency, as you do here by this differencing operation, that gives you the basis for the algorithm. But you can see how much better the spatial resolution is from the aircraft than from the satellite. The satellite has a footprint of about 40 kilometers. Our footprint was more like around 100 meters. So we learned a lot about not only the use of these frequencies, but also about snow distributions just by these aircraft experiments. Now, for the rest of the discussion, I want to turn our attention away from surface variables and speak more about the atmosphere. In particular, the important products of water vapor, moisture, liquid water, rain, and temperature to some extent. These are strip maps obtained a little more than 12 years ago in flying across a hurricane core. And you can see the effect of the hurricane core pretty well. There's an eye here where there's actually very little water vapor at all. I should say not water vapor, there's a fair amount of water vapor. Very little rain. And if you ever have a chance to do that, to perhaps participate on one of the NOAA hurricane flights, you realize that it's quite an incredible structure. The eye itself is typically 10 to 15 kilometers tall, and it's about that in diameter as well. And when you fly into it, it's impossible to miss. It's like a huge towering structure all around you. But you can see here we observed the rain bands of the hurricane very well. These bright areas are where there was rain in one of the local rain bands around the core. And that rain warms up the signature. Normally, if you didn't have the rain, you'd be looking right at the ocean surface, which is a good reflector. You'd see cold temperatures. When the rain gets into the field of view, it warms things up, and you can see it quite well. And from an aircraft, you can see it with a spatial resolution, again, on the order of a kilometer or so. Now, why is a kilometer so important with regard to rain? It has to do with the size of rain cells themselves. The atmosphere itself you could think of as a sheath around the globe that has a thickness of about 8 kilometers. And so it's rather natural to think that the size of convective events are also about that same size. There's a relation between the two. You'll rarely find convective events, except, for example, tornadoes, that have extremely skinny behavior relative to this 8 kilometers, or extremely broad, because they tend to decorrelate. So when you can observe things at about 1 kilometer or so, you've observed them pretty much at their native scale. And that's pretty important for environmental observations. But you can also see some interesting effects in here. These swaths were taken over several hours of flight time. We were on the NASA DC-8 aircraft, which is a flying laboratory of sorts. And we'd, of course, make turns and fly across, make more turns, etc. And you can see movement in the locations of the rain bands, and you can also see evolution in those rain bands. Turns out that rain doesn't happen for a long period of time. It's a dynamic process. And as it's happening, that cloud is being depleted of moisture. It's being pushed around by winds. And so the typical time scale of rain is roughly in the neighborhood of anywhere between, say, 5 minutes and maybe 25, 30 minutes. So you don't expect, for example, with a satellite in low Earth orbit, to fly over, see a rain cell, and then come back 12 hours later, which is the typical orbital cycle for low Earth orbiting satellite, and see the same rain cell. It's gone by then. Or that hurricane core has moved quite significantly. But when you have the opportunity to observe something and observe it again at its native time scale, in the case of rain, about 15 minutes or so, give or take, then you can really start to take that data and put it into predictive models that allow you to lock on to that event. And that's the frontier right now. That's the frontier from the standpoint of observing in space. It's being able to take microwave systems, which have this neat ability to penetrate down into the atmosphere to varying degrees, to have them operate with spatial resolutions down at that roughly atmospheric scale height scale, 10 kilometers give or take, and to observe events at roughly 15-minute time scales. That is the holy grail of observation in terms of providing data for weather forecasting. I'm going to get back to that in a moment, but I just want to show you a couple things we did with this data. This is our aircraft data. You can see it's conical swath. And what we got out of that are rain rates. So you can observe how much it's raining in millimeters per hour. And you can compare that with satellite data as well. So we actually validated the TRIM Tropical Rainfall Measurement Mission's satellite data using this aircraft experiment. You can see here, however, that we are fairly sensitive to changes, horizontal gradients on an aircraft, whereas in the satellite data that's not the case. A lot of this is actually artifactual from the satellite data because they're using a channel that doesn't really look through the rain very well. Now before I talk about this holy grail a little bit more, I want to just point out what it takes to calibrate one of these instruments. Because unlike a lot of imaging applications, our needs are down at the roughly 1/2 Kelvin or better precision, given a total noise that is typically on the order of 500 or 600 Kelvin or higher. And so I want to put that in perspective for a moment, but it requires us to do a lot of rather careful work in taking these voltage measurements that come out of this instrument and then interpreting them as brightness temperatures. Now, where does this 1/2 Kelvin come from? Generally speaking, if you want to measure the moisture variation in the atmosphere to a good degree of precision, one that a meteorologist will appreciate, it requires about 1/2 Kelvin of precision. If you want to measure climate variations in temperature, which as we all know are very much on the minds of people today, then we need to be measuring even more precisely. We need to be looking for changes in the Earth's atmosphere on the order of 1/10 of a Kelvin over a decade. So these are very small numbers we're looking at. How much overall energy does this receiver take in? Well, it typically takes in not only the Earth's terrestrial temperature, the equivalent energy of that, which is around 300 Kelvin, give or take, but also it takes in energy from its own little receiver in the form of additional noise. And that overall amount comes out to the equivalent of about, again, anywhere between 500 Kelvin or so for a good receiver, maybe up to even a couple thousand Kelvin. So let's say we're looking for a climate signature of 1/10 of a Kelvin, and we're looking for that signature in the presence of a total temperature of 1,000 Kelvin. That's 10 to the 4th. Very rarely do you have imaging systems that require 1 part in 10 to the 4th in precision. That's in the milliBel level of precision, basically. So a decibel is 1/10 of a bell, a milliBel is 1,000th of a bell. And so it brings us to a whole other series of ways in which we have to calibrate these sensitive devices. We utilize external blackbody targets. In other words, we literally point the radiometers at devices that emit very highly, in other words, reflect very little and therefore emit very highly. And if we measure their physical temperature, we know then their emission temperature. These are called blackbody targets. We typically have to have 2 of them for any radiometer, a hot and a cold one. That gives us the opportunity to determine a slope and an intercept of a calibration curve, a calibration line. Now, the problem with these external targets is that you can't see them too frequently. In our aircraft, for example, we need to be spending our time imaging the Earth, and the same thing goes for any satellite. You want to spend your time looking at the scene, not looking at targets. It takes a lot of energy and a lot of time to move a radiometer and literally to look at another target. That's something you want to do very seldomly. And in our aircraft practice, we typically do that at the end of every flight track, maybe 20 minutes apart. In that 20 minutes, a lot of drift can happen. And so what we do is we use what we call noise diodes to rather rapidly switch in references. Noise diodes can be switched in typically in a period of far less than a millisecond. And so if you take maybe 5% of your scene time and switch in these noise diodes, you can get a very common, very often, very frequent calibration. But you don't know exactly what their temperature is, and so you still need the external blackbody targets. You have to reference, in other words, these measurements to that measurement. Finally, even these blackbody targets have flaws associated with them. When you look at them with your antenna, there's, as hard as you may work at designing them, a little bit of reflection from them. Moreover, your antenna beam is not contained only within this cone that you might use to look at the target with. There are side lobes to the antenna, usually small, but nonetheless, these side lobes miss that target. How do you account for that? Well, what we do in the case of aircraft is we look at the cold sky. If you can turn the aircraft upside down and look at cold space, you've got an excellent calibration source. Its temperature is 2.7 Kelvin, and if you're high enough up in the atmosphere above any sort of other atmospheric emission, that's a nice stable 2.7. You can actually correct for the other atmospheric effect pretty well. And so how do you turn the aircraft upside down? With some very daring pilots. We actually don't go upside down, but we steer the instrument as far as we can to the side. We then give the pilots the go-ahead. It's usually on return with a light load of fuel. And the pilot rolls the aircraft about 70 degrees. Don't try this at home. From that, we can estimate then what we call the gain and the offset of the equipment by referencing. We reference the noise diodes to the external blackbody to the cold sky, and therefore that gives us gain and offset estimates on a very often basis, typically every 20 milliseconds, 50 milliseconds or so, give or take. So this is the raw data we get from the instrument, for example. This is a voltage that's coming out of our A to D converter. And in between here, where it looks kind of level, those are actually the scene observations. That's what's really interesting in making up the picture. And everything else is for calibration. These spikes are when we look at a cold noise diode, then a hot noise diode, and we do that very often. This is 1 minute of data. Then every so often, we'll be able to point the instrument at the hot target, and you can see the temperature goes up. And then we point at a cold target. These are the external targets that you can't look at very often, but nonetheless, they're very important. And we can then put those together to figure out what the gain and the offset is. So here's a typical radiometer gain estimate as a function of time. It's again 1 minute over here. I'm sorry, this is longer. This is 3 hours. This is about 3 hours. And what we have is a gain and an offset from the noise diodes. Those happen very frequently, so there's a lot of data in here. And then infrequently, we look at the external targets, and that pins down the noise diode gain and offsets. But you can see here that if we didn't do that, the gain of the instrument would be varying a whopping amount, 25% over this 3-hour interval. That would be an error, equivalent error of typically around 150 Kelvin, way beyond what we could tolerate. So these kind of calibration techniques are absolutely essential. They're used on aircraft instruments. They're also used on spacecraft instruments. This is a little blow-up of some of the data in this window over here. You can see where we pin down the temperature of the noise diodes with the external calibrations, and then these are the gains associated with the noise diodes. But even these, quite frankly, are fairly noisy. And if you look at the 6 sigma variation here, that 6 sigma variation turns out to be on the order of 1% or so. Even that's too noisy. So how do we go and further determine what the real gain is? We do it by knowing something about the characteristics of the instrument. We have to know something about how the gain normally drifts, and also something about how much on each one of these estimates is noise. And when we do that, we can set up what we call the optimal Wiener filter. It's a non-causal filter that we can run over this data post-flight. And we can then determine the best estimate of the gain. And this best estimate is in a linear minimum mean square error sense. It's as good as you can do with a linear filter. And typically that gets us down to the point where we can resolve 1/2 Kelvin variations and know that they're indeed 1/2 Kelvin from the scene and not from the instrument. And in applying that, then we can develop imagery like this. This is a series of maps observing sea ice. This is 18 gigahertz. We're flying, again, in this serpentine fashion. Some of the pilots call this mowing the grass for obvious reasons. And we can see, as we go from open ocean down here to pack ice, very significant variations in brightness and a lot of structure associated with the ice that's peeling off of this. This is, by the way, the Fram Strait, and it's the bottom of the so-called ice tongue in the Fram Strait. This is where all the ice in the Arctic eventually drains out and enters the Atlantic Ocean, where it then eventually melts. But what we're seeing is the remnant of the ice that's pushed out of the Arctic. Now, I've been talking a lot about aircraft experiments. Why do we like aircraft experiments? Simple matter of spatial resolution. Here's the same data in the previous slide, showing all the structure in the environmental signatures. And this is what you get if you were up on a satellite. And in fact, the satellite footprint is even larger. This is the satellite footprint, typically around 30 kilometers or so. And the resolution that we get from the aircraft is on the order of about 1/2 kilometer or so. So there's a lot more information you can get in studying this process. Now, can you afford to fly aircraft all over the Arctic to do this on a regular basis? Absolutely not. So far too much to demand. You can afford to do that with satellites when you get them in orbit. But you can still learn a lot about the effects of this, what we call spatial inhomogeneity, on the satellite signature and improve the development of the algorithms. Now, what's the Holy Grail here? The Holy Grail is microwave imaging and sounding, which is profiling, from geostationary orbit. Now, in the mid-1960s, we first put a camera up in geostationary orbit. This was a visible camera and allowed us to see for the first time clouds evolving. Spatial resolution was rather moderate, around 10 kilometers, but it did allow us to see regular changes. Unfortunately, ever since then, All we've had in geostationary orbit, which allows us to see, again, regular snapshots, is infrared and visible. And unfortunately, those don't allow us to see below the cloud tops. So where you have the most interesting weather on the planet, that is underneath the cloud tops, associated with hurricane eye walls, weather fronts, you have no ability to observe it on this time-resolved basis. If you enter now the possibility of doing the same kind of observation but with microwaves, you can select frequencies that allow you to observe down into that cloud to whatever degree you'd like. And that in some sense is what's needed right now. It's the ability to put a system in orbit in geostationary, where we're going to observe things on a regular basis, but yet see down through the clouds to all the various levels. This has actually been recognized. The National Research Council in 2007 got together and decided that, well, in the face of budgetary cuts, we've got to figure out what are the most important instruments that we ought to be building for space. They came up with a list of 10, and some of them had to do with measurement of climate variables. But one of them on the list was this instrument called PATH, Precipitation, Atmospheric Temperature, and Humidity, which was meant to be a geostationary microwave mission. So this whole concept now of geostationary microwave, vetted by the National Research Council, was one of 10 instruments that the U.S. must put up at some point in time. Now, what form it's going to take, we still don't know yet, but it's certainly needed. But what are the problems in going to geostationary orbit? One of the biggest ones is distance. At roughly 37,000 kilometers from the surface, any antenna beam that you have expands into a rather large footprint. And so you have to have a very narrow beam to be able to observe anything at these scales that we're interested in, 10 kilometers, 20 kilometers. And therefore, if you're working at microwave frequencies, where the wavelength is much longer than the infrared or visible, you've got to have a big antenna. And that has been a major cost driver ever since the idea of going to geostationary with microwave was explored. It was first explored back in the late 1970s. Once we observed the Earth from low Earth orbit with microwave, immediately the obvious thing was try to put it in geo. Well, if you do the calculation, and if you want to go to geostationary orbit at any of these various frequencies that we typically work at, all these have their various advantages and disadvantages. And if you want to have a certain spatial resolution, which is in this matrix, then you've got to have a certain antenna size. And you can see what happens immediately. If we want to observe, for example, at 89 gigahertz, and we want a spatial resolution of 10 kilometers, 15 meters is the antenna size. Now that's a pretty big antenna, especially recognizing that that antenna has to have a surface tolerance for it to operate of about 100 microns. So building that kind of a structure is extremely expensive, and it is really what's kept us from putting microwave in geostationary orbit since it was first conceived. Well, what frequencies would we like to use? What would make sense? Well, we want to go down low so we can see through precipitation to a great extent, but we also want to go up high so we can sort of slice through the atmosphere and see clouds up near the top. And we'd also like to work at particular absorption frequencies, absorption lines that is, oxygen, water vapor, so that we can measure atmospheric temperature. That's what we can do with oxygen here. And so that we can measure the amount of moisture in the atmosphere. And so it turns out that when you look at what nature has handed us in this spectrum, there are a few lines that make sense. There's this one here, which we use now regularly from low Earth orbit, but not from geo. And that's oxygen. There's another one here at 118 gigahertz that we use. Actually, we don't use this at all yet, but we would like to. There's another one at 183 gigahertz, which is important. That's a water vapor line. Another one at 380 gigahertz. And finally, one more at 424 gigahertz. This is pretty much what has shaken out of a lot of studies over the past 30 years on just what frequencies would make the most sense. And a lot of this was done as a result of aircraft studies as well, I would tell you. As a matter of fact, again, the work I did in the early 1980s was to explore this line for the first time and to determine what we could get from that line. Other people have done the other lines. This has led us to a system that has a lot of good characteristics. It's a compromise to some extent. It's a filled aperture reflector, about 2 meters in diameter, would be in geostationary orbit. It's got a mass of about 65 kilograms. It has channels at 54, 118, 183, 380, and 424 gigahertz. It's a Cassegrain antenna. And it steers its beams, performs the imaging, in other words, in the following fashion. It has a fast nodding and morphing subreflector that moves around rather rapidly. And that scans the beam very, very rapidly back and forth, typically with a refresh time of about 1/10 of a second and a scan time of about a second. So it's really doing something like this. And then another slower scan system that takes the whole system and moves the entire antenna. Kind of sweeps it across, just like the pilot on the aircraft mowing the grass, so to speak. So this is a fairly practical system. It does have some moving parts, and that's a source of concern. Could be built, we believe, for something like around $50 million and placed on a geostationary bus. And I mentioned before a vertical resolution. Well, what do we get out of these various channels? Here at 118 gigahertz, we can look to various heights in the atmosphere just by choosing the frequency offset properly. Same thing at 424 gigahertz. And we can do similar things in measuring the water vapor profile at other bands. So there's a lot we can do with these frequencies, and so it satisfies a lot of meteorological needs. These are images of what we would get if we had this system. And this is in particular at a frequency of 424 gigahertz, but 424 gigahertz very close to the line and 424 gigahertz far away from the line. And just by changing the offset frequency from that line center, you can go from opaque all the way to transparent, and you see very, very different effects. You're literally probing down to the vertical structure of that hurricane. Notice something interesting here too. At the high frequency, what we see is a warm area in the center of this hurricane core. It actually exists. It's called the hurricane warm core. It's the exhaust of the hurricane, and it contains temperatures typically on the order of 5 to 10 degrees C warmer than down below. It's never been observed in the infrared. This is the way the scan would work. Basically, we're rapidly scanning back and forth using this nodding subreflector, and we're taking the entire system and rather slowly scanning it back and forth in this serpentine fashion. And allows us to image swaths that are around 200 kilometers in width with 1 second per scan, about 1/10 of a second retrace. And you can also vary this. If you want a Nyquist sample densely, you can do that. If you don't need a Nyquist sample, but just need to scan an area in a more cursory fashion, you can also do that. When you have Nyquist sampled imagery, you can also sharpen the image to some extent. If you take an original image at 5 kilometer resolution and you blur it with a 30 kilometer spot size, what you can then do is perform an optimal linear estimate of the deconvolved image, and you can get back what is effectively around 22 kilometer resolution imagery. So this is image sharpening. It's a fairly well-known technique. You can do it in Photoshop if you like, and of course doing it here is very important as well. What you do pay for it, though, is you're also amplifying the noise in the image. So generally speaking, there is a price you pay, and this works well only for high signal-to-noise ratio cases. I'm going to skip this. It just tells us that we indeed satisfy a lot of meteorological specifications with this system. We can observe over a fairly large region in about 15 minutes. And I do want to say, too, that there are some competing technologies. One is the use of an interferometer. One of the biggest complaints about what I just showed you is we have to have moving parts on it. And there's a lot of people who complain. They think that moving parts fail in space. And so there's an interest in coming up with a system that has no moving parts. And that's the so-called interferometer. Here's the interferometer in New Mexico that we all know as the Very Large Array, the VLA. And this provides astronomical imagery. But you can take the same technique, put it in geostationary orbit, turn it upside down, and image the Earth with that. We actually have done that now. There's an instrument called SMOS, launched by the Europeans in space. It's the first spaceborne interferometer. See, it looks like the VLA, basically, a Y array of antennas looking down at the Earth. And This operates at a lower frequency than what we'd be doing in geostationary, but this is one of the first images from SMOS, showing the capability for us to use interferometry from space. So there's a lot of interest now in doing this from GEO, and a lot of people have been studying the sampling patterns of this instrument and looking at various other aspects of it. One of the biggest problems is that you have to have a lot of receiver elements, typically 300 to 600 receiver elements, and you have to cross-correlate the signals from every one of those elements in order to form an image. That generally brings you up to tens of thousands of complex correlators. And so the complexity of this, just in terms of the number of elements you have to have up there, the number of correlators, the power associated with those, the mass, that's driving people also in a direction to go back to the filled aperture system. So these are two competing technologies. There are a lot of trade-offs. I won't get into those in too much detail, but depending upon how you want to scale the system, the filled aperture and the synthetic aperture scale very differently. It's a lot easier to add additional channels to a filled aperture system, small cost, but it's very expensive to add additional channels to a synthetic aperture system. You need a whole new bank of correlators, basically. So this has led us to something called the geomicrowave pathway study, which I'm going to go over fairly quickly. It's to study how these two systems would perform in space. And not just what kind of pictures we get out of them, what kind of forecasts we would get out of them. That's really what sells the system overall, is how well it's going to forecast weather. So we've been developing something called precipitation locking, and I'm going to spend just the remainder here showing you a few movies of our simulations, showing a little bit about what these systems could see. And what I'm going to show you here, if this plays, there we go. This is a 24-hour movie loop with 15-minute time segments observed at 420 gigahertz. Now, this is the highest frequency of the system. And you can see that you see a lot of rather interesting effects. I want to point out that you're seeing effects whereby there are cloud bands moving into the hurricane and cloud bands moving out. What are those two from? It's from the cyclonic inflow that occurs at the base of any hurricane and the anticyclonic outflow that occurs at the top of the hurricane. At this particular frequency, you observe both of them. You go to a lower frequency that can punch through the clouds better and see deeper in, and you only see the inflow. I'm going to show you that. So here's a lower frequency. For the most part, all you see is the inflow because you're punching down to those lower regions in the hurricane where you're seeing essentially the rain bands down near the surface. You don't see that stuff up on the top that's anticyclonic. So this shows how you can actually slice through the hurricane. But what happens now when you observe it with a 2-meter antenna? You blur things out. That's just what happens. That's the law of diffraction. We can't get around that. If we can build bigger antennas, that would work. But of course, that's costly. I'm going to go ahead and just show you a little bit about what we're doing in the area of what we call precipitation locking and why this is important. We want to have imagery that's going to be sampled at a high enough time rate and a high enough spatial resolution so we can lock onto the hurricane. Because these are very nonlinear processes. If you're not locked down to it, then it's going to drift off, kind of like a phase-locked loop. In a phase-locked loop, if you don't sample the phase every cycle and adjust the oscillator, you basically lose lock. It's the same in meteorology, but on a slightly different scale. What I want to point out here is the sampling requirements for this locking are well satisfied by this geomicrowave system. And I want to show you a couple of quick slides that prove that. This is at 424 gigahertz, and we can see the hurricane evolving. These are 15-minute time steps. We can also see a slice through this hurricane of what we call the Jacobian. Now, I'm not going to spend much time on the Jacobian because we don't have the time, but the Jacobian is the derivative of the brightness temperature with respect to the various parameters of the hurricane, rain rate, temperature, etc. And what we see is a very nice smooth change in that Jacobian from time step to time step. We see it over here in this Jacobian, also in this one, which has to do with scattering, also in this one, which has to do with temperature. Nice and smooth. If we observed at 3-hour time steps, the Jacobian completely decorrelates. And it indicates how you need to have very rapid updates in order to be observing these systems and to keep forecast models locked onto them. Now we're running out of time, so I'm just going to say we are working on this with something called the hydrometric tracking simulator. It does all the things that are needed to generate these images, to blur them out, to produce then multispectral assimilations of quantities, and to look at how accurate we can then observe the actual data as well as forecast. And I think I'm going to end right there. We have a few other movies that we can look at a little bit later on, but let me just summarize in saying that microwave radiometers provide an important means of environmental imaging. And they work on scales very relevant for a lot of important applications: forecasting, monitoring, things like sea ice, for example, resource management. The airborne systems have played a major role in the development of the spaceborne systems. We've learned a lot more about processes on aircraft because we can essentially build these systems rather easily. Calibration is everything in radiometry, and it drives our requirements far more than most imaging systems. And finally, the holy grail here is to develop a geostationary microwave imaging system, and a lot of the aircraft data and the modeling that we're doing is leading up to that. Hopefully, by the end of this decade, we're going to have a system up. I think that there's a good probability that that'll occur. So thank you very much.
So we have time for one question or two.
How do you handle scan registration?
Georegistration. You have to know the angle that the instrument's pointing precisely, and basically that's not too difficult to do because the infrared and visible systems in GEO right now, the best of those systems have around 2-kilometer spatial resolution. So if we can just hop on the bus, so to speak, literally use the bus and use the pointing system, we should have no problem doing that.
What about the airplane base?
Now that's a little bit different because with aircraft the trajectory is not so regular. We do have inertial navigation systems that provide us data sampled, that is position data, heading data, location data, at about 60 hertz. And if you pay the price, you can get that data sampled to angular precisions of about 0.01 degrees. And that satisfies all your requirements. It's a very important issue, though, because it turns out that as these microwave beams see the Earth, typically what happens is if that beam changes its incident angle, just because of the Fresnel effect, the brightness temperature changes. And that derivative is about 1 degree Kelvin per degree angle. That's a derivative over an ocean. Over land, it's a little less. But if you're off by 1 degree in your angular registration, you're off by 1 degree in your brightness as well. And it does produce a lot of the noise in our images that we see. So getting down to about 1/10 of a degree in angular precision, or even better, about 100th, is quite frankly all you need. And those are able to be done with contemporary systems.
How bad is man-made contamination right now? How bad is it?
Of what aspect? Oh, thank you very much. That's a very important. I thought you mentioned. I thought you were talking about the atmosphere, which is a whole other question. But we are finding more and more that the anthropogenic signals that are being emitted by a host of sources, whether they be computers that are operating out of band that may not be sealed properly, whether they be cellular phone systems that have harmonics, or whether they be even legal transmissions that just are encroaching because of social and economic pressures on the open bands. We're finding that's becoming a very significant problem below 10 gigahertz and is even being noted at frequencies around 18 and 20 gigahertz in the current satellite records. It's ironic that when NASA launched its AMSA-E sensor, NASA and JAXA teamed on that sensor. They launched it in, I believe it was 2002. They immediately found that one of their channels was interfered with very severely and was unusable for global soil moisture measurement. Turns out they went to another channel, a higher